All right, SL1, we're finally going to start talking about 12.2 and talking about the unit circle, which is going to be a big part of our work today, tomorrow, and in 2021. So, the unit circle, guys, is not just a clever name. It's called a unit circle because it has a radius of 1 unit. So this is a distance of 1. Which means that this is the coordinate 1, 0. And then this is the coordinate 0, 1. If you kind of take that red line and rotate it around the circle. So that's 0, 1. This is negative 1, 0. And this is 0, negative 1. Now, we've been talking about radians and degrees rotating around the circle. So I thought I would fill this whole thing out with some very important spots on the circle that we're going to be using. First, in orange, I will label all the degrees around these spots. So here, this is 0 degrees. Then each of these are, well, they're not each a certain thing, but the important parts of the circle that we need to know are 30 degrees, 45 degrees, 60 degrees, 90 degrees is a right angle up top. Then 30 past that means this is 120 degrees. Then another 15 past that, or halfway in between 90 and 180, is 135 degrees. And then this is 150 degrees. Now, if I go 30 degrees, well, this is 180 degrees. That's a full 0, like a flat line. Half of a circle is 180 degrees. If I go 30 degrees past that, that means this is 210. Go another 15. This is 235. Then this is 240. No, what did I do wrong? Jolly, come on. Am I going to have to start this video over? 30 degrees, halfway in between 180 and 270 is 225. There we go. My bad. 225 degrees, which means this is 240 degrees. Then 45 past 270, that means this is going to be 315. Sorry, I skipped one in a weird order. That means this is 300, and this is 330 degrees. Oh, and then all the way back around is 360 degrees. Now, we're not going to be doing a lot of our work in degrees. And one thing I've noticed over the years of teaching unit circles is that if I throw out a weirdish radian, like, 7 pi over 6 or something, a lot of students will convert that 7 pi over 6 into degrees, figure where that is on the unit circle. But I don't think you should do that. I think you should just know that in this quadrant right here, the first 3, like the 30 degrees, is pi over 6, and then the 45 is pi over 2. I always remember that one because pi over 4. I always remember pi over 4 because 90 degrees up here, this is pi over 2. So halfway in between pi over 2 and 0 is pi over 4. And then 60 degrees is pi over 3. Now, I always say you don't have to be good at memorizing to be a good mathematician, but truth be told, I mostly have these big 3 memorized, because if you have those 3, finding other spots around the circle is really easy in terms of radians. You just have to count by those. So here's what I'm going to do. Pi over 6, I'm going to first fill out all the pi over 6's. So this spot right here is like 1 pi over 6. And then if I count by another pi over 6, that means this spot is 2 pi over 6. But 2 pi over 6 reduces to pi over 3. So this is 1 pi over 6, 2 pi over 6, 3 pi over 6, which is halfway in between, reduces down to pi over 2. So then this would be 4 pi over 6, and then this would be 5 pi over 6. So let me get rid of all those. That means that this is 5 pi over 6. Now, if I count by another pi over 6, that means this is 6 pi over 6, and then this spot would be 7 pi over 6. This spot would be 8 pi over 6, but we're actually going to use that for the counting by 60s, so I don't really care right now. 9 pi over 6 would be here, and then this would be 10 pi over 6. But once again, that's part of the 60s, so we'll get there. Really, the one thing you need to know is that a full 360 is like 2 pi, which is like 12 pi over 6. So if you go backwards by 1 pi over 6, that means this is 11 pi over 6 in terms of radians. Now, that was counting by pi over 6s. Now, 60 degrees is pi over 3, so let's count by pi over 3s. The first one would be 1 pi over 3, but then at 120 degrees, it'd be 2 pi over 3. Then 3 pi over 3, sorry, I'm trying to get rid of my highlights. 3 pi over 3 would be here, but that's the same thing as pi. And then another 60 degrees on top of that would be 4 pi over 3. So this is, once again, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. Then 5 pi over 3 is going to be another 60 degrees past that. So this is 5 pi over 3. And then another 60 degrees brings us back to full circle, which would be like 6 pi over 3. But 6 pi over 3 reduces down to 2 pi. 2 pi being a full circle. I don't like that arrow. Now the pi over 4s. Let's count by pi over 4s. Here's 1 pi over 4, 2 pi over 4. That means this is 3 pi over 4. So 135 degrees is 3 pi over 4. Then this would be 4 pi over 4, and this would be 5 pi over 4. So that means 225 is the same thing as 5 pi over 4. Notice I'm not converting any degrees here. I'm just counting by certain pi over 4s. So that's 5 pi over 4 is right here. This would be 6 pi over 4, but that reduces down to 3 pi over 2. And that means this is, 5, 6, 7 pi over 4. The one thing I haven't counted by, because there's a couple spots that haven't been labeled here, well, one of them right here is the 270 degrees, which I've kind of talked about, but we haven't labeled it. The way I always remembered that is that if this spot is pi over 2, that means this is 2 pi over 2. And then if you do another one, that means this is 3 pi over 2. Let me see if I got them all. Let me see. This is 0 still in radians and 2 pi in radians if you go full circle. Oh, the only other thing left is that half of 2 pi over here, that 180 is pi. There you have it. These are all the very important spots around the unit circle, both the coordinates of all the tops. And we notice we haven't filled out the coordinates of any of these guys. That's going to come more on Friday's lesson. But yeah, these are all the radians and degrees. So I really urge you guys to just think in terms of radians. That if it's like, you know, I throw out a 7 pi over 6, you're like, oh, that's pi over 6 past 6 pi over 6. So it's going to be like right here around 210 because pi over 6 is the same thing as 30. So it's 30 degrees past 180. The next thing I want to do is start talking about sine, cosine, and tangent. Well, no, I don't want to talk about tangent yet. Let's just talk about sine and cosine. Sine of theta, I need you guys to think of as the height of a triangle. And cosine of theta as the base of a triangle. Now, when I say triangles, here's what I mean. If I have some sort of theta rotation, regardless of whether or not it's in radians or degrees, let's say you rotate, you know, theta all the way up to this spot right here. So from here, this is your theta rotation. Now, any spot on the unit circle, you can always turn it into a right triangle by dropping a line down to the x-axis, a right angle line, and then the base would be this right here. So we know that the hypotenuse is 1. We know this because it's the unit circle, so every hypotenuse is going to be 1. But this height right here is going to be sine of theta, and the base is going to be cosine of theta. Now, there's certain spots around the unit circle that have the same sines and same cosines. One example of that is that if I take this whole triangle here, this orange triangle, and I flip it into quadrant 2. Oh, that's one thing I should maybe label is the quadrants. You guys, this is quadrant 1, and then it goes counterclockwise, just like the unit circle does, that this is quadrant 2, this is quadrant 3, and this is quadrant 4. So this triangle, this orange triangle in quadrant 1 can be flipped over the y-axis into quadrant 2 and would look something like this. It would have like the same height here. So it'd be like dropping it down here, still connecting it to the origin. Still a 90-degree angle. So your sine of theta is going to be the same with this triangle. But the theta rotation for that triangle, like the theta doesn't live right here. It's not connected on the negative side. The theta always starts at the positive x-axis. So if I was going to label the theta for that triangle, it would start here and go all the way to here. So that is the same theta. Or not the same theta. It's, I should use a different letter. It's like a, well, no, we'll say it's theta, but like this red theta and the green theta would be different numbers. But they would have the same sine value because both of those triangles have the same height. Much the same way if I was to take this positive theta rotation and actually do like a negative version of it. So let's use pink. So go this way with it, like this. You would get a triangle down in quadrant 4 that has the same cosine because both of these have the same base. Like the orange triangle and the pink triangle here, they both share that side. They share a cosine. They share the base of the triangle. So that means that this negative theta, sorry, this is getting messy, but this rotation here, which would be negative theta because it's going clockwise, not counterclockwise, would have the same cosine values. Now, the sine value would be the complete opposite. So, like, this sine value up here would be positive, but then down below, it would be the same number, just negative. So it's like, you can say this side here is going to be negative sine theta. Much the same way with this triangle over here, that it has the same sine as our original triangle here, but the cosine is just opposite. It's still the same distance, but it would be negative. So this is a negative cosine theta. Based off of all of that, there's actually these rules that the book comes up with. I don't think you really need to know these rules. I just kind of always draw a circle and figure out where the triangle lands and figure out if my signs are going to be positive or negative. But there are some tricks that some people use. I'm not a huge fan of these equations, but I'll give them to you. Sine of theta equals sine of 180 minus theta. Now, this is only when theta is in degrees. You could write the radian versions of these by doing like sine of theta equals sine of pi minus theta, and it would be the same thing if your thetas are in terms of radians. But the book gave them to you in degrees, so here we'll do that. Cosine theta is the same thing as cosine negative theta, and then we haven't talked about tangent yet, but I'll give it to you. Tangent is the same thing as tangent of 180 plus theta. So, if you think about all these triangles around the unit circle, so let's draw another one. You know, if you get a triangle right here, this is going to be your sine theta, and then the base is going to be your cosine theta. tangent is actually, you can think, like, it goes back to the SOHCAHTOA, that tangent is like opposite over adjacent, where this, if the theta is right here, that this is your opposite side, and this is your adjacent side. But in the unit circle, your opposite and your adjacent are sine and cosine. So there's actually a definition of tangent that says tangent of theta is equal to sine of theta over cosine of theta. The way I like to think of tangent is that it's not only opposite over adjacent, it's not only sine over cosine, but it's also a rise over a run. So tangent is a lot like the slope of the hypotenuse. It's the slope of this. It's not the distance, because the distance is 1. We already know the distance is 1 here. It's the slope. So, you guys, as this theta rotates around the circle, like, let's say I do another one here. Like, do you see how with that triangle that the sine has gotten bigger and the cosine has gotten a little bit smaller? In fact, all the way up here at the top, like if I get really close to the top, like the cosine gets very, very small. And in fact, if I get like a super duper skinny triangle right up here at the top, that's all sine, no cosine. That's a sine of +1 and a cosine of 0. Then when I flip over into this quadrant, I still, and you always drop a line down to the x-axis and connect it with a right angle. Never the y-axis. Always drop your line to the x. Now, my sine is still a positive number, but my cosine has turned negative. Because in terms of the x-axis, to the left over here is all negative values. So my cosine has turned negative. Then as my triangles go all the way around, like if they get closer and closer over to 180, like do you see how my sine of theta has gotten very small here and the cosine has gotten very large negative? When you cross over 180 into this quadrant down here, that means that the cosine, the sine is now negative because I've dipped below the x-axis in terms of the y, so that's negative as well. And the cosine is negative. So you start to see this relationship of like, in the first quadrant, sine and cosine are both positive, but then in the second quadrant, sine is still positive, but cosine's negative. And then in the third quadrant, sine and cosine are both negative, and then in the fourth, it's like what? The sines would be negative and the cosines would be positive? I always just draw a picture and reason it out, but there is this mnemonic, this trick that people use, and I will show you it. It's this. Let's get a little bigger. It's all students take calculus. So, all students take calculus. Which is almost true. No matter what you study in college, like you'll probably end up taking some sort of calc. Mostly true. You guys, the ASTC, this reminds you what is positive in each quadrant. So, I feel like this trick is like more trouble than it's worth sometimes, because it's like you have to remember the letters, you have to remember what they stand for, and then remember what the heck they're actually telling you. It's telling you what things are positive in certain quadrants. So here, this is all are positive in the first quadrant. So we'll say quadrant 1. Then in the second quadrant, the S stands for only sine is positive. Why is that a subscript? Come on, Jelly, what are you doing? So quadrant 1, they're all positive. Quadrant 2, only sine is positive. In quadrant 3, only tangent is positive. And then in quadrant 4, the C stands for only cosine is positive. I feel like you can reason these out just by figuring out where the sine and cosine are negative based off the x and y axes, and then your tangent is always sine divided by cosine, so feel free to use this trick if you want. I don't think it's 100% necessary. Example, find an obtuse angle that has the same sine as the acute angle, and then we're going to do 70 degrees and pi over 4. We're looking for find an obtuse angle that has the same sine as the acute angle. So generally for unit circle problems, I do a quick sketch of a circle for every single one. So, yeah, cool circle. Okay, I'll start here. 70 degrees is somewhere about here. That's like a 70-degree rotation about. So if we want to find a sine value, an obtuse sine value. So right now this is acute, this angle right here. That's acute. But we need to find an obtuse one that has the same sine value. So this is the sine of 70 degrees. That's the height of that triangle. I don't care what it actually is. We're not talking about the value of it, but we know it is sine 70. If you flip that into quadrant 2, so same triangle, but just flipped over the y-axis, this will have the same height, the same sine. Remember, sines are the heights of the triangles, so these two are the same. So the way I think we need to figure out what the angle is based off the reference angle. So the reference angle here is the shortest distance back to the x-axis. So this is a reference angle of 70 degrees, but the total angle will be 70 degrees back from 180, because this is 180 degrees. So that means this is 110 degrees. So the answer to this one is 110. That's an obtuse angle bigger than 90 that has the same sine value as 70. You could check it on your calculator, do sine 70 and sine 110, make sure you're in degree mode, and they should be the same thing. The second one is like the same problem, but we're going to do radians. So first, pi over 4. Remember that pi over 4 is 45 degrees, so that's halfway in between 0 and 90. So it looks like this. So here's our sine of pi over 4. Now, same process as before. We're just going to take that triangle, this one, and flip it over into quadrant 2. So that would look like this. Now, this still, like this angle right here was 45 degrees, so this will have the same reference angle of 45 degrees. But here, the total theta would be 45 back from 180, so that's 135 degrees. Oh, but we're not doing degrees. Oh, jolly, I did the thing that I told you guys not to do. Think in terms of pi over 4s, that this is like a pi over 4 back from, like, okay, this is the perfect opportunity to use the method. Pi, this spot is pi in terms of radians, but think of it in terms of pi over 4s is 4 pi over 4. Like, don't even think about it as pi. Whoopsie doopsie. So this is 4 pi over 4, which is the same thing as pi. So this is like 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which means this spot, theta equals 3 pi over 4, which is pi over 4 back from 4 pi over 4. So 3 pi over 4 has the same sine value as pi over 4. Without finding theta, find cosine of theta when sine of theta equals 3/5 and theta is acute. Okay, we got to talk about a tool that we haven't used yet. You guys, if you have some sort of triangle in the unit circle, we've already said the sine will be, or the height will be sine of theta, and the base will be cosine of theta, and we know the hypotenuse is 1 because it's a unit circle. You guys, this is a right triangle, which means you can use Pythagorean Theorem, which means sine squared theta plus cosine squared theta is equal to 1 squared, which is just 1. So if the sine of theta is 3/5, so let's draw a quick picture. So I don't know what rotation this is, but we'll just put it in the first quadrant and say that the sine of theta is 3/5. So the height is 3/5, and we don't know the base, but we know that the hypotenuse is 1. So we can say 3/5 squared plus cosine squared theta is equal to 1. Just use that Pythagorean identity. Square the top and the bottom, we get 9/25 plus cosine squared. Come on. Cos squared theta is equal to 1. Subtract 9/25 from both sides, so you get 1 minus 9/25. Then do a common denominator. So this is 25/25 minus 9/25, which is 16/25. And that's nice because those are both nicely square rootable. So we get cosine of theta equals plus or minus 4/5. Now, I did the plus or minus because we square rooted, and you always have to do that. But it says theta is acute, which means that cosine cannot be negative, because for cosine to be negative, I'll use a different color, that would mean it would have to be somewhere over here in quadrant 2 or 3 is where sines are negative, cosines are negative bases. But that would mean it would be an obtuse theta, and it says theta has to be acute. So if theta is acute, we're only working in quadrant 1. We don't care about these quadrants, which means I get to toss the negative and say that cosine theta is equal to 4/5. All right, I think that's it for that problem. Your guys' homework is going to be 12C 1 through 5, but don't do number 4. 4 is a bonus. Yeah, 1 through